All right, here's a quick primer on the difference between absolute convergence and conditional convergence. First, consider this theorem we proved. If a series has terms that are positive and negative, but we take the absolute value of all of its terms, if that series of positive terms converges, then the original series, which may have some negative terms, must also converge. All right, well, this is kind of related to absolute convergence. When a series converges absolutely, that means the absolute value of its terms as in a series would also converge. In other words, in the absolute convergence theorem, if you have some series where you take the absolute value of the terms and that converges, then the series of those terms converges absolutely. That's the relationship to the absolute convergence theorem. If this happens, then you have a series which converges absolutely. When you have a converging series, if you took the absolute value of its terms and it still converged, then this series doesn't just converge, it converges absolutely. So if that doesn't happen, if we have a converging series and we're wondering, does this series converge conditionally or absolutely, we can look at the series with the absolute value of terms. If that doesn't converge, if it diverges, then this converging series doesn't converge absolutely, it converges conditionally. So that's the definition of absolute convergence and conditional convergence. Let's relate it to some series that we've already worked with. This series we recognize as the alternating harmonic series. We can write it in summation notation like this, and we can prove with the alternating series test that it converges. So when we know that it converges, we can say, does it converge absolutely or conditionally? Well, if we look at the absolute value of these terms, we'd have 1 plus a half, plus a third, plus a fourth. And we know that that series is the diverging harmonic series. It's a P series with P equals 1. So this blue series, the alternating harmonic, converges, but its absolute value of its terms as a series doesn't. Therefore, it converges conditionally. And we've seen that when a series converges conditionally, we can rearrange its terms to get other values. So we know that the converging alternating harmonic series converges to the natural log of 2. But if we change the order of these terms in a way that we can clearly see this series uses every single term of this series exactly once. For the odd denominators, we have them all. 1 over 1, 1 over 3, 1 over 5, 1 over 7, and 1 over 9. So we include all of them. And for the even denominators, like 2 and 4, we have negative a half and negative a fourth. Next after that is negative a sixth and negative an eighth, and they're all here. Negative a half, negative a fourth, negative a sixth, negative an eighth. So every term in our original alternating harmonic series is covered here. And yet we show that this series, written in this order, won't equal the natural log of 2. Instead, it'll equal 1/2 of the natural log of 2, because we can do a little bit of arithmetic by grouping like this and then doing the subtractions and getting a half. And then a third minus a sixth is a sixth. 1/5 minus a tenth is a tenth. And onward. A seventh minus a 14th will be a 14th. And we can factor out the half. And that is the natural log of 2. So we have 1/2 times the natural log of 2. But we started with the exact same terms. We just rearranged them. So the exact same terms can be arranged to converge to the natural log of 2, or by changing the order but using the exact same terms, we can rearrange them to be 1/2 the natural log of 2. So this is only possible when a converging series converges conditionally. It's not the definition, but this is what's possible when you have conditionally convergent series. And you cannot do this with an absolutely converging series. All right, that's it. That concludes this short primer on absolute convergence versus conditional convergence.